Okay, hello everyone, and welcome to this Advanced Dynamics lecture. This is the first lecture, and we'll get started shortly. Okay. Okay, thanks for those chat messages. Kindly note that once the lecture is started, it will be much appreciated that everyone stays on mute and listens to the lecture attentively. Ideally, questions will be taken at the end of the lecture. If you notice that the screen has frozen or my video is frozen, you can unmute yourself, one of you, and let me know so that I can fix that. All right, so let's get started with today's lecture. So this is SE5046 Advanced Dynamics, and the instructor for this module is myself, Amar Behera, and you can reach me at my email, which is mentioned below my name. Up of dynamics, which you did last year, SE4017. SE4017 was a level 4 module where we studied a number of topics on dynamics, which were motion of particles, force and acceleration, force, work and energy, impulse and momentum, kinematics of rigid bodies, mass moment of inertia, and simple harmonic motion. I'm sure most of you will remember these topics. I know that simple harmonic motion was not covered, so we will cover that in this module now. At level 5, we'll look at some advanced topics in dynamics. And these are motion of rigid bodies, force and acceleration of rigid bodies, work and energy applied to rigid bodies, impulse and momentum applied to rigid bodies, rotor balancing, vibrations, and the modeling of dynamic systems. So we'll do some of the similar topics that we did at level 4, but applying them specifically to rigid bodies. And then we'll go on to look at some more advanced concepts such as rotor balancing, vibrations, and modeling dynamic systems. The textbook remains the same, which is Engineering Mechanics, Dynamics by Hebler. A list of the learning outcomes from this module. So at the end of this module, you'll be able to demonstrate knowledge and understanding of dynamics and vibrations of rigid bodies and systems. You'll be able to select and apply appropriate mathematical concepts, principles, and models to model solutions to engineering problems, and you'll be able to analyze engineering systems. You'll be able to apply the principles and concepts of dynamics to a design process, for instance. You will also acquire some practical skills. So using the laboratory experiment that you'll do during this module, you will be able to quantify and analyze the performance and behavior of mechanical structures and mechanical or electrical systems by acquiring and interpreting appropriate data. Finally, you'll work in collaboration with others and devise a plan to solve realistic engineering problems. Okay. In terms of the assessment, we will have a coursework assessment, which is based on a single lab, which will take place next year of 10%, and you'll also undergo an examination of 90%. The resources that will be made available to you are lecture. You'll also get a lot of practice questions in the tutorials. You have the textbook that has been referred to you, but also there are many other textbooks in the library. We'll do some formative quizzes that will not add up to your final score. So to be able to do these formative quizzes, I recommend that you should download the Socrative app, on your phones. And if you have your Socrative app, then from the next class onwards, we can do a small quiz that will test the understanding from the previous lecture. And it will also help you know how well you are progressing on this module. So you'll get continuous feedback that will then help you when it comes to the final examination, where again questions may be based on some of these formative quizzes. So it is definitely worthwhile to attend the classes and do these formative quizzes. And finally, be open with us wherever you do not follow. Send an email or contact us. It is always worthwhile to set up a meeting in advance. That will help me set aside time for you rather than you dropping in ad hoc, because we are continuously busy and in many meetings and classes. So set up a meeting and then I can help you. And it is very much an open door policy, even though it is a virtual open door now. So speak regularly and you will definitely see yourself to success at the end of this module. Okay, so moving on to today's objectives. What are today's objectives? Well, at the end of this lecture, you would have recapped the concepts of position, displacement, velocity, and acceleration, which you learned in Dynamics 1, which is level 4. And we'll just recap those, and you'll be able to describe these concepts mathematically and graphically. You'll also be able to, again, review the concepts of force, acceleration, and inertia. We'll also recap the concepts of work and energy. We'll recap the concepts of impulse and momentum, and we'll also look shortly at simple harmonic motion. Now in dynamics, the key is to have the concepts right. And if you have the concepts right, then you'll be able to think right and perform thought experiments, which then enable you to solve a dynamics problem. So typically dynamics problems have 4 layers to them. So you'll need algebra to solve dynamic problems. You'll need calculus. You'll need graphs to illustrate different variables such as position, displacement, velocity, acceleration as functions of time or against each other. And you'll need vectors to be able to solve the problem. So we'll use these ways of expressing the concepts regularly. If you're unsure of what they mean at any point, please ask. Okay, so I hope you're happy with this. So where is dynamics in the context of mechanical engineering or in the context of mechanics, which is key to studying mechanical engineering? Well, mechanics is the study of how bodies react to the forces acting on them. Now, mechanics can be divided into several sub-disciplines. One is statics, which you had at level 4. Statics is the study of bodies in equilibrium. The other is dynamics. Now, dynamics can be further broken down into 2 subtopics, kinematics and kinetics. What is kinematics? Kinematics is the branch of dynamics that is concerned with the geometric aspects of motion, while kinetics is a branch of dynamics which is concerned with the forces that cause the motion. Okay, so notice the key difference between the 2 words. Very often students will confuse these 2 words, kinematics and kinetics. So kinematics is only about geometric aspects. There is no Newton's laws there. It's just something that's moving. It has velocity, acceleration, displacement, etc. So just using the geometry of the motion, you should be able to tell how fast something is moving or whether it's accelerating, etc., etc. Whereas in kinetics, we look at the forces and we see how the forces are causing the displacement, acceleration, velocity, etc. Okay, so that is the difference between kinematics and kinetics. Now, before we move on to discussing kinematics, I want to show you a couple of videos which will get you warmed up for this module. The first is a robot by Boston Dynamics. Okay, was everyone able to view the video? Can somebody pop into chat and say yes?
Yes.
Okay, and you could hear the audio as well?
No. No audio.
No audio.
Oh,
No.
you hear audio? Okay.
Stuff.
I'll fix that now.
Yeah, they've already started trialing those robots in public in America in a few states now.
Yes, Boston Dynamics robots are quite popular, and I encourage you to go on YouTube and have a look at these videos. They will be very interesting for you to watch. Before I start
Have you
this,
seen the one when you...
I will change the sharing to. I'll change the sharings to the video. Then
Yeah, there's one where he has a gun as well. You get to shoot down range.
Yeah, this is the one thing they're doing for the army. It can go across snow and climb up stuff. It's not very nice, like.
Crazy, yeah.
I can start a Skynet, mate. That's what it is.
Terminator's coming to get you, mate.
Got my tinfoil hat at the ready here.
are you able to see the video? Just a moment. I think I have to enable the audio. Yep. Include computer sound. So that should do it.
Come on, we can't see the video. It's just you watching the video, I think.
Oh, you can see the video. Let's see. It's probably because the way I shared it. I think the sharing was okay. Is it? Can you see it now?
Yeah, it's come up now. Yeah.
Okay. And you didn't see it from the start, did you?
No, I presume you were just trying to solve something on the computer. So we've not seen the video at all on this one.
Oh.
This is sick, this.
Is it going through okay?
Yeah, we
Yeah,
can
we can hear it now.
Very good. You can hear it as well, yeah?
Yeah, we can hear it now.
Most space organizations, government or commercial, have set their sights too low. They've really built relatively small rockets. And Falcon Heavy is the first time that there's something that's arguably even in the super heavy class, or somewhere between heavy and super heavy. 5 million pounds of thrust is really crazy amount of power, more than twice as much payload as any other rocket. It can launch things direct to Pluto, no stop needed.
Hotels in the area are completely sold out.
Yeah.
Parking lots are packed.
It's like the first time something exciting has happened in rocket launch in a very long time.
Falcon Heavy is configured for flight.
T-minus 15, standby for terminal count.
SpaceX Falcon Heavy, go for launch.
10, 9,
All systems currently green. Set booster ignition.
5, 4, 3, 2, 1.
Side boosters, vehicle.
Landing burn has started.
Gotcha, I see it. Yeah, I got him. Right there, you right there. You've got to be kidding me! What?
Hopefully that was not too loud. Get back to the presentation. All right, so these two videos give you some motivation for studying advanced dynamics. And if you study advanced dynamics, then you should be able to participate in projects such as the ones that you saw. These are some of the extreme examples of where dynamics is applied. So yeah, so let's get on with the review of our material from level 4. So at level 4, we studied kinematics of particles. Kinematics of particles essentially describes motion of a particle. This involves position, velocity, and acceleration. So 3 quantities. Velocity is nothing but the derivative of position, whereas acceleration is the derivative of velocity, and hence it is the second derivative of position. You can also write another useful relation, which is acceleration equals v dv/ds. Now this is very useful to solve problems where you want to take time out of the equation and solve acceleration in terms of velocity and displacement alone. All right, hopefully everyone remembers these and some of the problems that we did around these equations. Moving on to a recap of vectors. Vectors have a magnitude and a direction. So on the top right hand side, you can see a vector v. So it has a certain direction, and there's an arrow in this direction. And you can break it down into perpendicular components such as Vx and Vy. To understand the importance of vectors, let us consider a person who is walking on a train in the opposite direction of the train's motion. Now let's say the velocity of the train is 35 meters per second, and the person is walking in the opposite direction at a speed of 1.2 meters per second. So we can write the velocity of train as v train equals 35 meters per second. And since the person is walking in the opposite direction, we can write the velocity of the person as minus 1.2 meters per second. So these are vectors because they have a direction. So v train has a direction and v person has a direction. So this is very important to note the difference between speed and velocity. Speed does not have a direction, it is just the magnitude, whereas velocity has a direction. So these vectors can be added. Now, if a person who is outside of the train, to him, what will be the velocity of the person? Well, the velocity of the person observed by this person who is outside the train is nothing but the velocity of the train plus the velocity of the person. So the net sum of these two velocities, we can add these two vectors to get the velocity of the person observed by another person from outside of the train who is stationary, and it works out to 35 minus 1.2, which is 33.8 meters per second. So a train is moving forward 35 meters per second. The person is going in the opposite direction 1.2 meters per second. So overall, a person who is stood outside watches this person move 35 minus 1.2, which is 33.8 meters per second, which also, if you think logically, you will come to that number. So essentially, by adding these two vectors, v train and v person, we are able to come up with the velocity of this person as seen by somebody who is outside of the train. Okay, so hopefully that was clear to everyone. Now consider the person walking across the train at 90 degrees to the direction of the train's motion. We know that the velocity of the train is 35 meters per second, and the person has a similar speed at which he's walking, but his direction is perpendicular to the train's motion. So if the person wasn't walking, he would look from outside to be along these dots which you saw on screen, to be walking in a straight line. But since he is walking and he is walking perpendicular, when you look at him, he will be walking along a slightly at a slight angle to the horizontal. Okay, and his movements are in these, is shown in these dark circles, whereas his movement, if he was not walking at all, is in the gray circles below it. Okay, so you can see that there is a slight deviation in his position due to his velocity, which is perpendicular to the train's motion. So can we find out what where he is and at what angle he is moving? Well, yes, we can. So the velocity is, of course, the derivative of the displacement. In 1 second, the person moves 35.02 meters. So you can see here, if you show the vectors that show the motion of the train and the person. So in 1 second, the train has moved 35 meters. In 1 second, the person has moved 1.2 meters. So in effect, he has moved along this hypotenuse of the right triangle, which is 35.02 meters. And how do we get that? Well, it's nothing, it's simply by using Pythagoras theorem. So 35 squared plus 1.2 squared, square root of that. That gives you the speed of the person. And if you then add the angle at which he is moving, you get the velocity. And the direction is neither in the direction of the train or perpendicular to it. It is at an angle of tan inverse 1.2 divided by 35. Okay, so 1.2 is his motion, 35 is the train's motion, and 10 inverse 1.2 divided by 35 gives the angle at which he is moving, which if you plug it into your calculators will come out to be 1.96 degrees. Okay, so when you make such calculations, be careful. The care you need to exercise here is that sometimes the calculating tool that you're using will not output in degrees. You'll get an answer in radians. If you get an answer in radians, then you have to convert it to degrees. Okay, so you may have to convert radians into degrees by taking into account that pi radians of 3.1416 is equal to 180 degrees. Right, let's learn a few more things about vectors. The idea of vector addition can be accomplished by splitting any vector down into orthogonal directions. So you can take a vector such as A and split it into perpendicular directions. So consider two vectors A and B, which are to be added. So these vectors can be split into any orthogonal directions. The aligned directions are added, then recombined to give the new vector. So let's say we want to add two vectors A and B. A has two perpendicular components, AX and AY. B has two perpendicular components, BX and BY. So we've broken them down and shown using arrows. Now we add the two vectors. So if we add the two vectors, we get this net resultant vector, which is shown in red here. Okay, and it is nothing but the sum total of the components in the x direction and the sum total of the components in the y direction, and you add them together with the direction. So this was going up and this is going down. So net sum is this much going up. Here we had AX in this direction and BX also in the same direction, so they just get added. So the net X component is AX plus BX, and net Y component is this AY minus BY, which is this much. And if you add them up, and if you join the end of this vector to the end of that vector, you get the net resultant vector. Okay, that's vector addition. It's important to note that any two orthogonal directions will give the same result. So if you broke it down not along X and Y, but along another two perpendicular directions I and J, even then you'll get the vector result to be the same vector. Okay, so regardless of whether you use X and Y or some other perpendicular directions I and J, you will get the same vector you can see here on top and bottom. All right, so that was vector addition. So how can we write it down formally? So let's say vector A had a component AI in the X direction and AJ in the, let's say, I direction and J direction. So we can write A as AI I hat plus AJ J hat, and we can write B as BI I hat plus BJ J hat. So net sum of A and B gives us AI plus BI I hat plus AJ plus BJ J hat. So that is your A plus B vector. Okay, hopefully clear to everyone. So now let's look at the key equations emerging from our kinematics studies in level 4. So if we use Cartesian coordinates, displacement can be written as the components in the I, J, and K directions. So let's say these are aligned with three axes X, Y, and Z. Then we can write R as Rx I hat plus Ry J hat plus Rz K hat. Now if we take the derivative of this, we get the velocity. So we get drx dt I hat. So that is the velocity in the x direction. Dry dt j hat, that's the velocity in the y direction. And drz dt k hat, so that is the velocity in the z direction. Likewise, if we take the derivative of the velocity, so this whole quantity drx dt is nothing but vx. So if we take the derivative of the vx, we get dvx dt I hat, so that's acceleration in the x direction, dvy dt j hat, that is acceleration in the y direction, and dvz dt k hat, that is acceleration in the z direction. Now we can have, instead of Cartesian coordinates, we might have tangential and normal coordinates. So for instance, if you have a ball that is rotating in a circle around the center, so we can have tangential velocity for that and normal velocity that is directed towards the center of the circle. In that case, the velocity works out to be ds dt in the tangential direction, ut, okay, and in the normal direction, the velocity is 0. And acceleration works out to be dv dt plus v d theta dt. So the angle that it's moving along the circle. So v d theta dt un. So that gives you the acceleration. Or you could write it as dv dt ut plus, we know that the centrifugal acceleration is v square over rho, where rho is the radius of curvature in which the object is moving. So you can write it as dv dt ut plus v square over rho un. Likewise, for the radial transverse directions, if we have radial and transverse directions, then we can write the velocity as dr dt ur plus r d theta dt u theta. So note the component in the theta direction. So if there is a change in the angle with time, so we get a component r d theta dt u theta. So you'll typically get this if you're moving in a spiral, for instance, and coming down. So we saw that video last year. If you remember that, a train coming down from the top of a mountain down to the bottom. So it comes down in a spiral, and there you can use these radial transverse coordinates. And acceleration then is the derivative of that. So that gives us d square r dt squared minus r theta dot squared. That's the acceleration in the radial direction. And the acceleration in the theta direction is r d square theta dt squared plus 2 dr dt d theta dt. Okay, so that's a summary of all of the kinematics on one slide. Now, moving on, we can now discuss kinetics. So kinetics is all about Newton's laws. So dynamics is essentially mostly Newton's second law. And we know that Newton's first law, which is mostly related to statics, it is that every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. So if an object is at rest or it is moving with a uniform velocity, then it will continue to move at uniform velocity or be at rest unless there is something that compels to change the state due to the forces that are impressed on it. Now Newton's second law states that force is equal to change in momentum per change in time. For a constant mass, force equals mass times acceleration. So this is essentially the cornerstone of dynamics. So if you understand Newton's second law well, you'll be able to solve all dynamics problems. Note the concept of inertia here. Inertia is nothing but how inert or how resistive is the object to changing velocity. So if an object has high mass, it then implies that it has high inertia. So for instance, if you look at the equation F is equal to ma, if m is high, if the force remains the same, the acceleration is lower because acceleration is F divided by m. So higher mass means the object is more resisting to motion or change in its velocity. Okay, so that is a basic implication of Newton's laws. Now Newton's laws can also be applied to rotating objects. If you rotate a particle, that also requires effort. So there is a rotational equivalent to linear inertia, and that is nothing but moment of inertia. So if F is equal to ma is the equation for linear systems, for rotational systems, we can write a similar equation, which is m is equal to I alpha or d squared theta dt squared, where m is the moment, I is the rotational inertia, and d squared theta dt squared is your rotational acceleration. Now, the units of force are newtons, whereas the units of moment are Newton meters. The units of mass is kilogram, whereas the unit of rotational inertia is kilogram meter square. The unit of acceleration is meter per second square, whereas the unit of rotational acceleration is radian per second squared. Okay, everyone remembers? I presume so. You also used these equations in your experiment on energy springs and flywheel, where you did the flywheel experiment and you were plotting torque versus alpha. So that was nothing but this right-hand side equation. The next concept that we studied at level 4 was work and energy. So work and energy concept, the work and energy concept is similar to the first law of thermodynamics. Now, the first law of thermodynamics tells us that energy is neither created nor destroyed, but it can change form and move. So we can carry out energy accounting and energy balances. And it is this same principle that is also applied in dynamics, and it helps us solve many dynamics problems. So the key knowledge in this is that the work done is nothing but transfer of energy by work, and a very simple way of expressing this is force times the distance. So if you have a force that moves an object by distance, then the work done is nothing but the product of the force and the distance. Some useful examples of work done. One of the most useful examples is work done by gravity. You see it all over the place. So it is also known as gravitational potential energy. So if I drop a glass bowl from the top of my table to the ground, if the ground is hard, on impact it will break. So when it has gone down by a certain height, then it has lost some potential energy, which was the gravitational potential energy, and this is converted into some velocity at the time of impact with the ground. Okay. So this gravitational potential energy is nothing but a product of the mass times the acceleration due to gravity and the height at which the object is there. So that is how it is quantified. So higher the height of an object above the ground, higher is its gravitational potential energy. Likewise, we can talk about work done on a fluid. So this is also known as pumping work. So work done on a fluid can be expressed as the product of force times the area of cross section times the length over which the fluid moves. So P is the pressure here times the area of cross section times the length over which the fluid moves. So in fluids, often pressure is a good way of quantifying or of measuring the flow, and if you multiply that with the area of cross section and the length to which it moves, then you get the work that is done on the fluid. You can express it also as minus P dV integral. So A dx gives you a cross-sectional volume, and if the pressure is varying as well, so you can bring it inside the integral, and you can add small amounts of P dV to get your work done. I'm sure you'll see more of this in this year's thermodynamics and heat transfer. The other quantity that is useful is the work done by friction. So frictional force is typically mu times the normal force. So if mu is the dynamic coefficient of friction, and there is a normal force that is acting on an object F. So mu times F is the friction force. Now this force times the displacement gives you the work done by the frictional forces. We also talked about kinetic energy at level 4. So kinetic energy is when an object has motion. It can be of two types, linear kinetic energy and rotational kinetic energy. So if an object is moving with the velocity v, its linear kinetic energy is given as half mv squared. If an object is rotating with an angular velocity omega or d theta dt, So then its energy is half I omega squared or half I d theta dt squared. Likewise, we can also have strain energy. Strain energy is also known as elastic energy. So when something is stressed, then it has strain. So a material is stressed, then it has strain. If this strain is given as epsilon, and if this material has a Young's modulus y, and the area of cross section A, and the length of elongation is dx, then the strain energy stored in a material which has been stressed by dx is epsilon y a dx. Okay, and you can also have spring energy, and spring energy is quantified as half k x squared. So what I have done is I've shown in these two a list of 1, 2, 3, 4, 5, 6, 7 key formula that will need time and again in solving dynamics problems. So no matter where you go for your internship or later professional work, remember these 7 formula. You'll use them over and over and over again. And if you're not clear how to use this formula, then you'll struggle in solving problems involving dynamics. Okay. So that's about the different types of energy. Commit them to memory and also understand the physical meaning of each. The next concept that we talked at level 4 was impulse and momentum. So we talked about a force being applied for a very short period of time to an object, and that leads to momentum transfer or a change in momentum. So a good example of momentum transfer or impulse would be two balls colliding with each other, and these two balls could be coming at each other from different directions, and they collide and then they move away in other directions. So this would typically be described using an equation such as this, which is the force times the time integrated over the short time interval between T1 and T2 during which there is an interaction between the force. That integral gives you the change in momentum, which can be written as m times delta v. So this linear impulse is defined as the integral of f dt T1 to T2 or I impulse. The momentum is defined as L momentum, or it is equal to the mass times the velocity. So remember this, impulse is the integral of force times the time over the time interval. So you do the integral between the times with which the object interacts with the force. So integral T1 to T2 f dt is your impulse, and it leads to a change in momentum, which is quantified as m times delta v. So you can also write this in vector form as bold I is equal to integral T1 to T2 bold f dt, and that is equal to m times bold delta v. Okay. Likewise, you can talk about impulse for rotational problems. In rotational problems, you'll interact with the moment for a short interval of time. So that interaction, some of the products of the moment with the small time intervals, if you sum them all up, it can be written as an integral T1 to T2 mdt, and that is equal to mass times the change in the cross product of r times v. So m delta r cross v, that gives you integral m dt T1 to T2. Okay, so that's a summary of impulse. Now let's move on to simple harmonic motion. So simple harmonic motion is a very special type of oscillation. A very common example is a pendulum. I'll show you a video that will explain this better. Okay. Are you able to see the video? The screen of it?
No.
No?
No.
Okay. So Teams has an issue in showing up all of the open files that I have, and that is creating a problem. Teams is not very good at recognizing all of the items that I have. Let's close now. If I say, if I just, yeah, can you see it now?
Yeah.
Yeah, I did for a second.
Yeah, very good. Just let me see if I can include the computer sound as well. Include computer sound and desktop, and I'll move. Yep, it should work now.
A pendulum is simply weight suspended from a pivot such that it can swing freely. A pendulum moves to and fro about a point, and hence it shows oscillatory motion. The time taken by a pendulum to complete one oscillation is called its time period. Let us calculate the time period for a given pendulum. Here we have a pendulum and a stop clock. Now we will count the time it takes to complete 10 oscillations. Swing the bob to one side and leave it. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10.
It's about 13 seconds.
Oscillation is a motion that repeats itself regularly, so it took 13 seconds to complete 10 oscillations. So the time period for the pendulum is 1.3 seconds per oscillation. Now we have shortened the length of the pendulum. We will see the effect on the time period. Let's swing the pendulum and start the stop clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10.
Less than 10 seconds.
Now it took 8.5 seconds to complete 10 oscillations. So the time period for the shorter pendulum is 0.85 seconds per oscillation. Hence we note that the time period of a pendulum depends on the length of the pendulum.
So that's typically what you would, that is the sort of motion that you'd analyze in simple harmonic motion. So the time period of the pendulum is proportional to square root of L, so 2 pi root L over G, and hence as we shorten the length, the time period fell. So you can do even, you can set up many complex systems that exhibit simple harmonic motion. So as the name says, it is harmonic motion, that is there is some harmonicity in the motion. For instance, here you saw the motion being sinusoidal in nature. So if you plot the displacement against time, you'll see that you get a sine wave. So this is a typical motion that you'll see in simple harmonic motion. Physical relationships in simple harmonic motion lead to sinusoidal kinetic relationships in terms of position, velocity, and acceleration. So if you take a derivative of a sine wave, you get a cos wave, that gives you the velocity. And then you take the velocity derivative of the velocity, you get another sine wave, so that's the acceleration. So if the acceleration of if the position was varying as a0 sine omega t, then you'll get the velocity as a0 cos omega t, a omega cos omega t by taking the derivative, and then you get a omega squared sine omega t as acceleration. So that's how you get your relationships for position, velocity, and acceleration in simple harmonic motion. In dynamics, we are using our understanding to develop relationships for specific systems. And in this course, we'll develop our understanding further to cover more general oscillations and vibrations. So I'll cover the part on simple harmonic motion and also take you further into vibrations, which are critical to designing many different machine elements, such as your machine tools in the workshop that you see, such as your lathes, milling machines, shapers, planers, cutters, etc. So everywhere you use the understanding of vibrations to design mechanical systems. And in advanced dynamics, we'll explore these. So to summarize today's lecture, in previous studies, we have focused on items which can be considered as particles. We understand the relationship between position, velocity, and acceleration and can represent these terms in vector form. We can work with Newton's laws of motion for particles in linear and vector forms. We now understand, after level 4, the concepts of impulse and momentum as an alternative approach to applying Newton's laws of motion. So the concepts of impulse and momentum give you the same results as Newton's laws, but it's a slightly different way of expressing it mathematically. We can also apply the concepts from our first law of thermodynamics, which is work and energy, to dynamics problems. And we have encountered simple harmonic motion and understand why some dynamic systems are oscillatory. Of course, we'll explore this further in this module. Now, while that is the end of the basic lecture, there are some questions that I've got which you can try out. So there are some questions on vectors, and there are some questions in your Principles of Engineering textbook that you might have, and some more questions that will help you practice and get ready for advanced dynamics. So I'll post these questions on Moodle after the lecture, and you can try these out. I'll also post this lecture online, and that will help you warm up for this year's advanced dynamics. So that essentially ends this lecture, but what we'll do now is listen to any questions that you may have. Okay. Does anybody have any questions? Yes, Stephen says something. No, thank you for the recap. So I guess everyone is gearing up for their weekend. So thanks to all of you for joining in on a late Friday afternoon. Sure, this well, I know that this period of pandemic has been difficult for many of you, but we will get through this together. Yes, Charles has his hand up. Charles, yes, you can ask a question.
Hi, Ahmad. I'm just wondering, did we get marks for the sort of optional assessments that you handed out?
Oh yes, so I will mail them to you shortly. So
excellent, thank you.
Monday. Yeah.
Cheers,
But
mate. Thank you.
was not everyone managed to get around to doing the optional assessment, but I can totally understand because of the pandemic. You're all trying to cope with the new normal. So those who are submitted will get a mark on email, and you can keep this mark as a future reference as well.
Excellent, thanks, Sam.
Okay, anything else? All right, so on that note, I will stop this recording.